So circles, equation of a circle, let's start with what a circle actually is. It's basically this round shape, pretty obvious. Center is h and k, so that's the center of the circle. We have a radius, which is the fixed distance that every point on the circle, xy, is from that center. So I have three things. I have points on the circle, which are xy, the center of the circle, which is hk, and the distance between any point and the center is the radius. And you can represent that with an equation, which is x minus the x coordinate of the center squared plus y minus the y coordinate of the center squared is equal to the radius squared. And if you remember, when we had derived that equation, it came from the Pythagorean theorem. So that's a circle with center hk and a radius r, like a pirate, r.
And you forgot one very important thing, mate. I'm Captain Jack Sparrow.
Anyway, so center of the circle, central angles. Turns out central angles, like this angle O, the measure of angle O is exactly equal to the measure of its intercepted arc, AB. So that's very convenient. Whereas inscribed angles, or angles formed by chords and a tangent, where that vertex is on the circle, it's half. So if the vertex is at the center, it's exactly equal. The vertex is on the circle, it is half. So we have the measure of angle B is equal to 1/2 the measure of arc ADC. And for the second one, the measure of angle 1 is equal to 1/2 the measure of arc AB. It's also true that the measure of angle 2 is 1/2 of arc ACD. So it's those two, half its intercepted arc. When a general angle, if I don't know if it's central or inscribed, and I just have some angle floating around on the inside of the circle, it is actually the average of its intercepted arcs, and it's the arc intercepted by that angle and its vertical angle. So those two arcs would be the ones I use to find the average of angle 1. So the measure of angle 1 is equal to 1/2 the sum of those two arcs, which is AB plus DE. Okay, so it's half those two arcs. When I have angles outside the circle, rather than half the sum, it's going to be half the difference. So I'm going to take, in each of these, it's the same situation. I'm just going to do measure of angle 1 is 1/2 BC minus AC. Okay, so rather than the sum, it's the difference. For angle 2, it would be PQR minus PR divided by 2 would give me angle 2, and 1/2 XY minus WZ would give me the measure of angle 3. Scrolling down, a couple of theorems related to circles you should be aware of. It's that congruent chords cut congruent arcs, which is a biconditional statement saying that if you know that, if you know these chords are congruent, then I know that this arc is congruent to this arc. Okay? And vice versa, if I knew these arcs were congruent, I could conclude that these chords were congruent. So it's a biconditional statement. If the diameter of a circle is perpendicular to a chord, then the diameter bisects that chord and its intercepted arc. So what that means is that if I know that this diameter is perpendicular to the chord, so given this stuff, I can conclude that arc DG is congruent to arc GF. Okay, so that's this arc is congruent to this arc. That's one conclusion I can make. I could also conclude that DE segment is congruent to EF. Okay, so I know that this segment is congruent to this segment. And also, if I throw a point in here, say A, I would also know that these two arcs would be congruent to each other as well. So DA would also be congruent to AF. So there's a lot of congruence things that I can, statements I can make from that. Keep in mind, I'm just going to clean up this diagram to point something out. You can also use this for a radius. If you only had this radius, and you knew it was a radius, well, you would know it was a radius, and the radius is perpendicular to this chord, then you could also conclude that these are congruent and that these two arcs are congruent as well. So not just for a diameter, but also for a radius. If one chord is perpendicular to another chord, then then. It's basically the converse of this statement. If these two chords are perpendicular, then JK has to be the diameter. So it's kind of going the other direction. If they're perpendicular, then I know one of them is the diameter. Okay, last bit of theorems. If SR and ST are tangent to a circle, then this kind of gives me statements for related to lengths. My pen does not seem to be working. There we go. If RS and TS are tangents, then the segment RS is going to be congruent to TS, so tangents have equal lengths. Congruent chords are equidistant from the center, so they are at the same distance or equidistant from the center of the circle. Okay, that means that these two chords, CD and AB, are congruent. Then I know that the length EG and the length EF are congruent. So they are the same distance, or this distance measurement here is equivalent for those two chords. If two chords intersect inside the circle, well, then the product of their lengths is equal to each other. So what that means is that segment AE times segment EB is equal to segment CE times segment ED. Okay, so the product of their component segments of the chords is equal to the product of the component segment of the other chord. So it's a way of getting length relationships. If two secants intersect outside the circle, then, well, it's basically the same kind of relationship, except my parts are going to be different. It'll be AE equal to EC, and I'm going to be multiplying them times the entire secant lengths. So it's AE, this external segment, times the entire thing, EB, is equal to EC times this entire segment, ED. Okay? Finally, if I have a tangent and a secant intersecting outside the circle, the tangent segment squared, AE, is equal to the external part of the secant segment, EC, times the entire secant segment, ED.